In lesson 2.3, we're going to look at right triangle trigonometry as it relates to similarity, and briefly we'll touch on some of the special right triangles. Much of this will be a review from what you learned in geometry class, but it is very, very important for what we are about to do moving forward with circular trigonometry and precalc. So the first important thing to remember is that right triangle trigonometry comes from triangle similarity. That is a really, really important thing to understand. And I'm going to sort of take you through that in a second. And in our case, we're just focusing on right triangles, so they will all have an angle of 90 degrees. So let's take a look. If I have some triangle, let's say triangle A, B, C, and this triangle, let's say, has a side length of 3, of 2, and by Pythag, this would be square root 13. We have a 90 degree angle, and let's call this angle 40 degrees and 50. And now that might not be realistic based on the side lengths, but let's just roll with it. If I have a dilated copy of this triangle, and for our purposes, let's pretend that I'm able to draw a triangle that is twice as big, and let's say that this is triangle DEF, and let's say that triangle DEF has side lengths of 4, 6, and 2 square roots of 13, and has the same angles, 40 degrees and 50 degrees. So we would say here that triangle ABC is similar to triangle DEF. Let me take triangle DEF and let's change its color to make it easier to keep track of. Make it green. Okay, so here we would have a scale factor of k is equal to 2, right? One is twice as long, or the side lengths are twice as long as the other, but the angles remain the same. And the important thing here, and where trig comes from, is there's a constant ratio between corresponding side lengths in each triangle. And hopefully you had an opportunity in geometry to do an exploration of this and sort of come to this conclusion. But that is super, super important. That is the idea. Because these are similar triangles, there's this constant ratio length. So if I wanted to compare like side BC and BA, well, I could say BC over BA, which is 2 over square root 13, should be equal to EF over ED, the ratio of the corresponding sides in DEF, equals EF over ED, EF being 4, ED being 2 square root 13, and we can see that 2 over 1 square root 13 would be the same as 4 over 2 square root 13. Those are equivalent ratios. And I could pick any set of sides that are corresponding and do this. So I could say the ratio of BC to AC, 2 over 3, is equivalent to the ratio of EF to DF, 4 over 6. Because the triangles are similar, their corresponding parts are in the same ratio, their side lengths. And then the last, if I wanted to do more, I could keep finding different combos. Maybe I would compare the hypotenuse, square root 13, to the side of 3. So I could say square root 13 over 3. And I could say that that would be equal to the hypotenuse of the second triangle, DEF, 2 root 13, and the bottom side, DF, 6. And root 13 over 3 is the same thing as 2 square root 13 over 6. So this main idea checks out, and it's this really important idea that there's a constant ratio between corresponding side lengths. And that's where trigonometry is built from. So in trigonometry, in right triangle trigonometry, if we have some right triangle with an acute angle theta, and it doesn't matter how big this right triangle is. It could be the size I drew first. It could be some bigger copy of it. The point is, because we have a right angle and an acute angle theta, well, by angle, right, the last angle must also be congruent. So we have two similar triangles. And we can define the sides relative to that acute angle theta. So I can call this my opposite side. This is, I'm going to call my hypotenuse still, and this I'm going to call my adjacent side. And it would be the hypotenuse, opposite, adjacent, relative to my acute angle theta. And so I can define these ratios of side lengths relative to my acute, or one of my acute angles, which we call theta. Key word here is ratios. It is ratios of side lengths. So I can set up a bunch of trig functions that tell me the ratio of side lengths for some acute angle. So for example, we call this sine ratio. We say sine of theta is equal to the ratio of the opposite to the hypotenuse. We say that cosine of theta is equal to the ratio of the adjacent to the hypotenuse. We say tangent of theta is equal to the ratio of opposite over adjacent. And the thing is, so long as these are right triangles, theta describes one possible similar triangle. Like if I know I have a triangle here and it's a right triangle and this is 20 degrees, it's only possible that this is 70, and I just have one triangle, no matter how big or small it is. By similarity, the corresponding sides, remember, must be in that same ratio. So that's the big idea behind trig. And so there's another thing that we are going to add now, though, for precalculus. And those are called the, let's do it in purple, those are called the reciprocal trig functions. So we're going to add in another set of trig functions here. But they're basically the same idea. They're just the reciprocal. So they allow us to take the ratios and flip them upside down. And the functions are called cosecant of theta. And I'll write that word out in a minute. And it is simply the reciprocal of sine. So it is equal to the hypotenuse over the opposite, the ratio of hypotenuse to opposite. There's a trig function called secant of theta, and it is the reciprocal of cosine. Its ratio is the hypotenuse to the adjacent. And finally, there is the cotangent function. Cotan of theta is equal to the ratio of the adjacent to the opposite. So you'll note that the ratios between each pair are just flipped, hence the word reciprocal trig functions. Now, adding to this, I can also say that 1 over sine is equivalent to the cosecant ratio, cosecant of theta. So spelled out, CSC is cosecant, and I'll show you why. If we look at 1 over, and sine theta we know to be O over H, so 1 over O over H, and I can rewrite this as 1 over 1 divided by O over H, and then rewriting this, I can say 1 over 1 times the reciprocal, there's that word reciprocal, H over O, which is just H over O. So my cosecant function is equal to the hypotenuse to the opposite. And that's why we call it the reciprocal function of sine. Additionally, we can say that 1 over cosine of theta gives us the secant function. SEC spells secant, or stands for secant, which is equivalent to 1 over A over H. And if you follow that line of math, we'll end up with H over A, the reciprocal. And finally, 1 over tangent of theta gives us the cotangent function, cotangent of theta, which is equal to 1 over O over A, 1 over tan, which is equivalent to A over O, the reciprocal. So that is a little bit of new information. Probably didn't see that in geometry class. However, it's not too bad. It's just the flipped version of the trig functions, the reciprocals. One little thing to be careful of is that sine goes with cosecant. Cosecant is the reciprocal of sine, not secant. So one starts with an S, the other starts with a C, so that can be a little bit confusing and just, I don't know, it seems natural to do it one way, but it's a little counterintuitive. Cosine goes with secant. Again, little counterintuitive. You would think it might be a little different. And then tan goes with cotan. That one's a little bit more obvious. All right, so let's look at an example using all of our new reciprocal trig functions. So let's say I have some right triangle, and let's use one of our classics. Let's use the 3, 4, 5 Pythagorean triple. And let's pick an angle theta, and we know this is a right angle. And say I want to get all 6 trig ratios. So say I want sine theta, say I want cosine theta, tan theta, cosecant theta, secant theta, and cotan theta of my angle theta in this right triangle. And relative to theta, we know that 3 is the opposite, 4 is the adjacent, and 5 is the hypotenuse. So sine is opposite over hypotenuse. Simple enough, it is just 3 over 5. Cosine is adjacent over hypotenuse, 4 over 5. Tangent is opposite over adjacent, 3 over 4. And then the reciprocal trig functions, cosecant, recall, is just h over o, right? H over o, which is just the reciprocal of sine. So it's 5 over 3 instead of 3 over 5. Secant is the reciprocal of cosine. It is h over a. And in this case, that would be hypotenuse of 5 over adjacent of 4. So it's 5, 4. You can see it's the reciprocal of 4/5. Cotan, you guessed it, is 4/3. It is the adjacent over the opposite. So that's how our reciprocal trig functions come into play. Relatively straightforward, just kind of have to remember what they are, but otherwise not too bad. Okay, I want to highlight a couple more key things, but that is just about everything you need for this lesson. I want to refresh your memory of special right triangles, and I want to highlight 2 things about trig and similarity that are important. So let me box this off. So key idea 1 here is that if I have some right triangle with an angle, we'll call it alpha, and an angle beta. That's supposed to be alpha. Let's try that again. So that's the symbol alpha, that's the symbol beta. Well, then it is true that sine of alpha is equal to cosine of beta. Okay, because relative to alpha, this is the opposite, and this is the hypotenuse. And sine is equal to the opposite over hypotenuse. But relative to beta, this is the adjacent, and this is the hypotenuse. So we're describing the same ratio. Like either way you describe it, cosine or sine, it's this side to the hypotenuse. It is the opposite of alpha, it is the adjacent of beta, but we describe the same ratio. And to see this happen with an actual triangle, let's make one up here, and let's say we have 2, 3, root 13 again. Let's call this 40 degrees and 50 degrees. Well, it would be true then that the sine of 40 degrees has to equal the cosine of 50 degrees. Again, this triangle is not real. I'm sort of imagining these angles and sides, but the idea is true. So sine of 40 relative to sine, opposite would be 2, so that would be 2 over the hypotenuse of square root 13. But relative to the angle 50 degrees, if we call that our angle, well, the adjacent is 2, and the hypotenuse is root 13, so cosine of 50 is also 2 over root 13. So we see that these two are the same. And that goes to what the word cosine kind of derives from. So cosine is the sine of the complement. Okay, and that's an E for complement. And recall from geometry that complementary angles are angles that sum to 90 degrees. Okay, so the sine of some angle is equal to the cosine of its complement. And that's because with 90 degrees being our right angle, there's only 90 degrees left to go around. So whatever this angle is, this one will be its complement, and the cosine and sine of the complements have to be the same. So that's a key idea number one to have. Another important idea is if I take some angle, let me just draw a random angle, and let's call this A, and I call angle A, let's call it theta, and I drop a perpendicular to the initial side of A, and I call this B and C. And then let's say I draw another perpendicular to the initial side, and we call this D and E. Well, then it will be true that triangle ABC is similar to triangle ADE by angle-angle similarity, because we have each triangle. So if I redraw off to the side, triangle ABC has theta, it has a 90-degree angle, and thus has angle-angle, meaning the last angle will have to be the same. If I look at triangle ADE, it's a little bit of a bigger version, but it must be similar because, let's do ADE, it has 90, it has theta, so the last angle must also be the same. Because of that, all the trig functions of these two triangles must be equivalent. So say I wanted to do sine of theta, I could say that that is equal to the opposite BC over the adjacent BA. Or I could also say it's equivalent to the opposite DE over the hypotenuse DA. Okay, and I could do that for every single set of angles here. So I could say like, or not angles, trig functions. So I could say cosine theta would be like AC over BA, but that's also the same as AE over DA. So I could do this for every single set of trig functions, but the idea that if I have this angle with two rays that go forever, no matter where I choose to drop this perpendicular, all those triangles are going to be similar, and thus all those trig functions are going to produce the same ratio. Okay, similarity, ratio, trig functions, these are all the things that you want to understand coming together. All right, so that sums up trigonometry and what you're going to do with it. There's some key ideas there. Last thing I want to cover is just a recap of the special right triangles. Okay, so let's write this out. Special, quote unquote, special right triangles. And I'll tell you why they're considered special in a second. But realize that these are, again, just an extension of similarity and trigonometry. So if you recall, one set of our special right triangles is I won't do the whole triangle. Let me do a nice one. Yeah. So the 45, 45, 90 right triangle. And that is also the isosceles right triangle. These two side lengths are some equivalent length x, and our hypotenuse then is x times the square root of 2, which is also kind of like saying about 1.41 times as long as the legs. The hypotenuse is that much longer. It doesn't matter if we draw a small one or a large one. No matter what, if we have a 45, 45, 90, then that is the case. And so if we think about the ratios, if I wanted to do like say sine of 45 degrees, well, that would be the ratio of the opposite to the hypotenuse, so x over x root 2, which is equal to 1 over 1 root 2, or just 1 over root 2. If I wanted to, like oftentimes we choose to rationalize our denominators, I could multiply by root 2 over root 2, giving me in the numerator just square root 2, and then in the denominator we would get root 2 times root 2, which is 2. We would also, though, have cosine of 45 is the same thing, because the opposite and adjacent are both x. So I get x over x root 2 equals 1 over root 2 equals root 2 over 2. Tan of 45 degrees would be equal to the opposite over the adjacent, which is x over x, which is just 1. So that's actually very useful. But the important thing to realize is this special right triangle that you probably have some familiarity with, just an extension of similarity and trig. So that's great. And then there's a second special right triangle set, the 30, 60, 90 right triangle, which would look something like this. If the hypotenuse is 2y, the side across from the 30 is 1y, so it's half as long. And then the side across from 60 degrees is given by y times the square root 3, which is approximately 1.7y. So it's about 1.7 times as long as the shortest side, which is half as long as the hypotenuse. And so if we go through and we do these ratios for this, we could say sine of 30 is equal to, well, the opposite to the hypotenuse. So that would be 1y over 2y, which is just 1 over 2. We could say that cosine of 30 is equal to the y square root 3, the adjacent, over the hypotenuse, 2y, which is just square root 3 over 2. And we could say that tangent of 30 degrees is equal to 1y over y root 3 is 1 over root 3. If we would like to rationalize our denominator, we can multiply by root 3 over root 3. And this is going to give us square root 3 over 3. We could also do these functions for 60 degrees. And I think I will, just to get you some repetitions of seeing what happens. So if I do sine of 60, well, that is going to be y root 3 over 2y, opposite over hypotenuse. So we'll do y root 3 over 2y, which is just root 3 over 2. Does that look familiar? Sure should, because here's root 3 over 2, here's root 3 over 2, cosine of 30, sine of 60, sine of the complement produce the same ratio. So if we were about to do cosine of 60, why don't you tell me what you expect that to be? It should be the same as sine of 30, or 1/2. So let's find out. Cosine of 60, the adjacent to 60 is 1y. The hypotenuse is 2y, which is just 1/2. Very good. What about tangent of 60? What would you expect here? How do you think that relates to tan of 30? Well, tan of 60, opposite of 60 is root 3, and adjacent to 60 is, y root 3, and is 1y. So we just get root 3 over 1, or just root 3. Now, it's not as obvious that these are linked, but remember that this came from 1 over root 3, and now we have root 3 over 1. So the complement of the tans are just reciprocals of each other also. So that's good. And we can look at, because we're going to be doing so much math in radians, our special right triangles in radians. If we have our 45, 45, 90, that is pi over 4 is 45 degrees, pi over 4, and then 90 is pi over 2. So that's what it looks like in radians. Still has the ratio x root 2. Doesn't matter that we're in radians, it's just a different way of expressing the angle measures. For 30, 60, 90, there we go, 30, 60, 90. But if we wanted to express it in radians, I wonder if it'll let me click on this. 90 degrees we said was pi over 2. 30 degrees is pi over 6, and 60 degrees is pi over 3. And then we still have the ratios y, 2y, y squared root 3. So that's a look at the 30, 60, 90, and the 45, 45, 90 in radians. The last thing I'm going to do is just refresh your memory on why these are quote-unquote special, where they come from. First one is 45, 45, 90 is half of a square. Why did that not accept my square? Let's try again. Doesn't like it. Come on, buddy. There we go. All right, so there's my square. And if I have a square, let's call it side length 1 and 1. And I'll draw a hypotenuse, making these angles 45 and 45. If I want to know the length of my hypotenuse, I'll use Pythag. 1 squared plus 1 squared is c squared. 1 plus 1 is c squared, 2 is c squared, and the square root of 2 is c. So we have 1, 1, 1 square root 2, or x square root 2 gives us the ratio there. So the important thing, the reason why we like this is because it's half a square. Squares are a really common, important shape with really useful properties. So having the special right triangle that's half a square is useful. Similarly, we have another one. So we have half an equilateral triangle. And this is where the 30, 60, 90 comes from. So if I attempt to draw an equilateral triangle, and if I draw a altitude, so it's perpendicular, let's say the sides of the equilateral triangle are all 1. We know the angles of an equilateral triangle are equal, so they're all 60. And at the top, I've bisected the angles, so I get 30 degrees. And I've bisected my base, so I get 1/2. And so to find the height here, right, I can use Pythag also. I can do 1/2 squared plus, we'll call it b squared equals 1 squared by hypotenuse. 1/4 plus b squared equals 1. B squared is going to be equal to 3/4. B will be the square root of 3/4. Property of square roots over division, I can say root 3 over root 4, aka b equals root 3 over 2. Okay, and if that's the case, b is root 3 over 2, well, now we have a right triangle with the proper ratios. We have 2y, 1y, and then y root 3, where root 3 times 1/2 is root 3 over 2. So that's where they come from. Again, equilateral triangle, very important shape, has many useful applications, and that's why this 30, 60, 90 is really important also. Okay, so hopefully this was a useful review of trigonometry, special right triangles, and how it all relates to similarity. This is really, really important information for your ability to progress through Precalc. So make sure you feel really solid on these fundamentals. Thanks for watching.